Hello everyone, my name is Zhang. It's been an honor to come to IJCAI to present my work here with the title Solving the Swing Up and Balance Task for the Acrobot and Pendubot with SAC. I'm under the supervision of Akira Satori on this project, and we are from Technical University of Munich in the Laboratory of Product Development and Lightweight Design. And I want to split my talk into these parts. First of all, the motivation, and then my methodology, which is SAC plus LQR. And then I will show the results from the simulation phase and the real system phase. And of course, I want to talk about the future world I want to explore. And finally, the acknowledgement. First of all, the motivation. The control system that we are dealing with today are becoming more and more complex nowadays, and reinforcement learning methods are becoming very popular in controlling complex dynamical systems. These two pictures that I put here, on the left, this thing is called ant, and on the right is the famous dexterous hand rolling a dice in his hand. And these two simulations are all trained with IJCAI under the NVIDIA Omniverse environment, and it's using reinforcement learning methods. And for why is reinforcement learning methods so popular among robotic control? I think we can find some hints within the definition of these terms. First of all, reinforcement learning is about let an agent learn how to make decisions by interacting with an environment and have feedbacks in the form of reward functions. And the control method we are using in this task can be categorized into optimal control. And optimal control is a method that optimizes a defined performance measurement, like normally a cost function. And our method here, reinforcement learning plus optimal control, can create an adaptive system that can have the advantage of reinforcement learning agents and, of course, the optimal control methods. Then I want to talk about my methodology, which is SAC plus LQR. SAC is for swing up and LQR is for stabilization around the goal point. And first of all, I want to explain a little bit about SAC. Because SAC is a very basic reinforcement learning method, so I won't talk about too many details for this. SAC is a short version of Soft Actor Crtic. I want to talk about Actor Crtic structure first. Actor Crtic is a structure that separates decision making and value estimation into two networks. The actor part has to do with taking the action after evaluation of the value, and the critic has to evaluate whether the action taken by the actor is good or not. And the soft part in the SAC algorithm is called entropy regularization. Entropy is a word which describes how random a random variable is. And entropy regularization here refers to add a bonus rewards every time in accordance to how random that policy is. And this is a deep reinforcement learning which uses neural networks for actor and critic part, and is also model-free. And there is one reason that we choose Soft Actor Crtic, because it is designed specifically for continuous state space and action space. And it's turned out to be very stable according to previous tests. And one other reason that we choose SAC as our algorithm is because this team has done a benchmarking work on the model-based reinforcement learning. And for the benchmarking part, they use model-free reinforcement learning algorithms, including SAC. And they have done some simulation work on Acrobot, which is similar to our task here. So we choose SAC as our first candidate. And now it comes to our methodology. what is SAC plus LQR. And the most important question is how to switch between SAC controller to the LQR controller. And for those who are not from the control area, I want to talk a little bit about LQR controller. And to use a LQR controller on a nonlinear system is like have to follow the following steps. First of all, you have to linearize a nonlinear system around a working point to x dot equals ax plus bu. Here, x refers to the difference between the goal state and the current state. And we can derive the LQR controller out of the Crtic equation and can give such a form, u equals minus k times x bar. And to make it stable, because LQR can only work on a linearized system, so we have to deal with the stability problem. It's common to use Lyapunov function to deal with this problem. We form this Lyapunov function, v equals x bar transpose s times x bar, and we have a lower limit, which is 0, and we have an upper limit, which is rho. We have this designed variable for this. And for asymptotically stable Lyapunov function, we have to make the first derivative of the Lyapunov function smaller than 0. And we have to find an S matrix and rho to make the Lyapunov function satisfy these two requirements. And in the state space, as I show here on the left, we can find some state space points that satisfy these requirements. And we use an ellipsoid shape to encounter all this, to include all the state space points that fulfills the requirements. And we use an ellipsoid shape to make it simpler for us to determine whether a state space point is inside of a catchable area, which is a region of attraction area of the LQR controller. And here comes to the reward shipping problem. Regarding the reinforcement learning method, we designed a 3-stage reward system. The first thing is a quadratic reward function on position, velocity, and torque. It is very similar to a LQR controller, and we penalize on the position difference, on the velocity difference, and torque usage. And I want to talk about the third reward first, which is when the agent reaches the ROA of the LQR controller, and we give a handsome reward. And because this is the ultimate goal of our system, to let it swing up to enter the LQR ROA area, so it can be caught by LQR controller, we give a very handsome reward, something like 1E5. And because it cannot learn to reach the ROA of LQR controller during the learning process, so we add a second level reward, which is when the agent swings up to above a certain line, we give a certain level, so it fills the gap between the first level of reward function and the third level of reward function. So it can learn to reach the ROA like on itself during the learning process. And here I want to show you the learning curve. And because Pendubot is relatively easy for a swing up and stabilization, so I give a 2E7. And you can see here there is no significant improvement from time step 1.2 E7. And the time step for the whole training process is 2 hours. And for Acrobot, it is very difficult to reach a good result. So I gave it in this training process a 3E7, and you can see that at 3E7 is still learning, and it's already cost me 3 hours. So when dealing with this problem, I warm start from a pre-trained model, and I train more steps on that. And eventually, at the total time step about 5E7, I reach a feasible model for this. And then I want to show you the results on simulation phase. The first thing is the simulation on Pendubot. As you can see, it's very, very smooth. And when you look at the graphs on the right, the swing up time is about 0.9 or close to 1 second. And the Pendubot is like very smooth. However, the control signal is noisy. So it has been a problem transferring this agent directly to the real system. And here is the simulation results of the Acrobot. As you can see, it swings up and stabilizes like very steadily. And however, at this trial, the agent swings up and it's go beyond 2 pi limit, and you can see here the torque change is also very, very severe, and the whole control signal is also very noisy. I think it's the born problem of like model-free reinforcement learning, because it learns to swing up and stabilize, but it doesn't care about how noisy the control signal is. Now let's talk about the real system. When we are transferring from a simulation to real system, there are a lot of problems happening. What makes that real system more complicated? I have found these problems. First of all, is time delay, and because there is always a connection problem between the controller and the real system, which is the models. And I measured the time delay in this case like 0.015 seconds. And because time delay is very lethal in this problem, because if we have larger time delay, it will harm the very basic idea of reinforcement learning, which is a Markov chain. If we don't have Markov property, the reinforcement learning algorithm doesn't work. And there is a torque tracking problem, because we're using a control frequency of 400 Hertz, and the control frequency is high, so the torque tracking is only around 80%. For example, if I give it a 5 Newton meter, and it can only reach 4 Newton meter in the given time. And there is, of course, always going to be a model uncertainty problem and other disturbances, for example, friction. And there are other challenges that's being posed on our training process is the competition rules, because the velocity has to be under 20 RED per second, and the position has to be under 2 pi, which means we cannot do a swing up like I showed you in the Acrobot simulation. It has to swing and go back, and like this. It cannot do like this. And I want to show you the successful version before I show you the successful version of the real system, I want to show you how did I transfer from the simulation phase to the real system phase. We use a checking environment, which is noisy simulation, and we add some. We make the noisy simulation as close to the real system as it can be, and we add the time delay, and we add the torque responsiveness, we add friction compensation for this, and every time we train a new model from the simulation phase, we check it in the noisy simulation. If it works, it's ready for transferring into a real system. If it is not, we have to go back and change and tuning and other things until it is suitable for noisy simulation. Let me show you the results. This is the model that eventually works on the real system, and it looks good in the noisy simulation. I mean, it's as close as it can be to the real system, but it still has some kind of difference. Yeah, here is the field test for Pendubot swing up and stabilization, which is successful in this time. As you can see, it swings up like within 2 pi limits and within 20 RED per second. However, the LQR catches, but it doesn't stabilize so perfectly. like as I showed you in the noisy simulation part, that indicates that there is still some kind of difference between the noisy simulation and the real world system. And as I can tell you, the success rate of the system is 40%, 4 out of 10. And there are three criteria, three things I can talk about is like one good thing, one medium thing, and one bad thing. The good thing is the swing up time for the Pendubot is very impressive, which is 0.67 seconds, and within 20 RED per second speed limit, which is really fascinating. And one satisfying criteria is the energy consumption is 37.12 J. It is in the middle of all the leaderboards results. One bad thing is talk smoothness, which I mentioned multiple times before. It's 0.74, which is not that good. The average score of my system is 0.298 because only 40% of successful rate. And the best score is 0.767. If this can stay successful all the time, it will be a good results, but it cannot. About future work, the first priority have to be the improve the success rate of Pendubot swing up and stabilization. One thing we would like to try is to use some method to penalize on the talk smoothness. For example, the current thing that we are thinking of is to use the talk as a input, as a part of the state space to train on that and to penalize on that. And maybe use acceleration as a part of the state space and to train on that. And of course, Pendubot is only part of the task. We would like to accomplish some successful swing up and stabilization for Acrobot as well. Of course, I will follow the path that we are having now and to see how the result goes. I mean, though Acrobot is like a little bit more difficult than Pendubot, I think it won't be any problem to achieve that in Acrobot. And of course, I want to try some model-based reinforcement learning methods because model-based RL methods have certain advantages. For example, they require less episodes to do the learning. For example, we need 1E6, 1E7 time steps and countless episodes to achieve a workable policy. And I want to try some model-based reinforcement learning methods. And of course, the goal of our task is to compare the performance of model-free and model-based reinforcement learning and to maybe to summarize the advantage and disadvantage between these two methods, and especially in robotic control. And for acknowledgements, I have to thank the IJCAI for the funding, and I have to thank Professor Markus Zimmermann from my laboratory, who is not